We're going to look at these two distributive property problems and decide if they have answers that are quadratics. Okay, so in number one, we're just distributing an x. So x times 4x is 4x squared, and x times negative 7 is negative 7x. No like terms, so that's simplified as much as possible. Number two, we distribute the 5. 5 times 3x is 15x, and 5 times 8 is positive 40. Again, no like terms. It's simplified as much as possible. So are those answers quadratics? One of them is, okay? Only number one is a quadratic. The reason we can tell it's quadratic is because it has x squared. But the reason the other one is not quadratic, the reason it's a linear expression, is because we never multiplied an x times another x. Okay? So in number one, we multiplied a linear times another linear and got quadratic. Okay? In number two, we just multiplied a constant by that linear expression. All right, 4 through 7, we're going to just multiply. Since each of these is a binomial times another binomial, we'll use what we've been calling the FOIL method. Okay, so first times first, x squared, outers, negative 9x, inners, positive 9x, and last, negative 81. The middle terms, negative 9x plus 9x cancel, so we're left with just x squared minus 81. Number 5, x times x, x squared. Outers, negative 2x. Inners, positive 2x. And last, negative 4. Again, the middle terms cancel. We're left with x squared minus 4. First times first, 36x squared. Outers, negative 30x, inners, positive 30x, and last, negative 25. Again, the middle terms cancel, so 36x squared minus 25. And lastly, number 7 here, first times first, 49x squared, outers, negative 7x, inners, positive 7x, and last, minus 1. And just like the previous 3 problems, these middle 2 terms cancel each other out, so we have 49x squared minus 1. Now, we hopefully noticed that the exact same thing happened in each one of those, that the 2 middle terms, the OI part of FOIL, the outers and the inners, resulted in opposites. So those 2 middle terms canceled out, and we were left with just a binomial rather than a trinomial. All right? So number 8 basically just asks which one of the coefficients, a, b, or c, equals 0, and it's, of course, the b coefficient. But the reason that happened was we had binomials of the form x plus a times x minus a, where we were, the constants at the end were just opposites of each other. And when you have that, when you have 2 binomials in this form, it always results in what we call the difference of 2 squares. Difference because it's a subtraction problem, and 2 because it's a binomial. Squares because each of the terms is a square, a perfect square. Okay, so we're going to look at a few of those and compare them to similar binomial multiplication problems that don't result in the difference of 2 squares. So like number 9, part A we multiply x minus 13 and x plus 13, but B we're doing x minus 13 squared, so the same thing twice. So how do these differ? Well, in part A here, when we do first, we get x squared, outers, positive 13x, inners, negative 13x, those will cancel, and then the last, minus 169. So when we cancel those middle terms, we're left with x squared minus 169. All right, now when we do part B and we're multiplying x minus 13 times itself, first times first looks the same as above. Outers, instead of getting one positive and one negative for the outers and the inners, we get both of them as negative 13x. And then the last, instead of being negative 169, is positive because the signs of those two constants are the same. So now, rather than canceling the two middle terms, we combine them and end up with x squared minus 26x plus 169. All right, same situation in number 10, except for the part B, instead of having double minuses in the parentheses, we have double addition. So let's look at this one. This top one should be our difference of two squares. Let's verify that. So we get first our x squared, outers positive 8x, inners negative 8x, last negative 64. So x squared, middle terms cancel, minus 64. For part B, the binomial squared, right? Really what we're doing is x plus 8 squared. We do first times first, x squared, outers, 8x, inners, another 8x, and last, 64, positive 64. The middle terms are alike. We add 8x and 8x to get 16x. So what we see here, and you can put this in your own words in number 11, when you have one of each sign, it's the difference of two squares. So it results in a binomial that is always a subtraction sign in between the two terms. For both part B's there, we have perfect square trinomials that result from squaring a binomial. All right, now we're going to factor. Okay, so now we're going in reverse. We're going to look at a trinomial and try to break it apart into two binomials. Now, the way I've been suggesting you attack this, first, of course, you look for a GCF. If there's no coefficient shown in front of the x squared, which we see in most of these, then you're not going to have a GCF. So we make this little magic x here. In the top of it, we write our desired product. That comes from multiplying a times c. So 1 times negative 45 is negative 45. The desired sum is the middle term, the middle coefficient b, so negative 4. And now we're looking for two factors of negative 45 that have a sum of negative 4. Okay. So again, I got the negative 45 from doing a times c, and the negative 4 comes from the b. So what two numbers can I multiply with the result of negative 45 and add together to get negative 4? Well, to multiply and get a negative product, I have to have one of each sign, one positive, one negative. If I want to add those together and have a result of a negative 4, then the absolute value of this negative number has to be larger. Okay? So which two factors of 45 are different by 4? And the answer to that would be 9 and 5. I keep the 9 as the negative because it has a larger absolute value than 5, and I want my overall result to be negative 4. So whenever we do not have any coefficient, or whenever the coefficient of x squared is 1, then these two factors we found can jump right into the factored form x plus 5 and x minus 9. And of course, the order you write those doesn't matter. So if you wrote x minus 9 times x plus 5, that's exactly the same thing. All right, number 13, we have the same desired product, negative 45, but a different sum, negative 12. So now we need, again, a positive and a negative factor, but this time they need to be different by 12. So that's 3 and 15. I want positive 3 minus 15 to give me negative 12. So that's x plus 3 times x minus 15. And number 14. This time, we again are looking for negative 45 as our product, but we want a sum of negative 44. So what two factors of 45 are different by 44? And that would be positive 1 and negative 45. So x plus 1 times x minus 45. Remember, if you're ever in doubt about your factored expression, just FOIL it back together, make sure it equals your original trinomial. All right, number 15. Again, we're going to stick with this, keeping the C term the same for all three problems, and just changing the B, the sum that we're looking for. So in 15, we want product negative 72, sum of negative 1. So that means these factors of 72 have to be different by 1. That would be positive 8 and negative 9. So x plus 8 times x minus 9. Number 16, still working with negative 72, but now we want our sum to be 14. So this would probably not be one of the multiplication tables that you learned in 3rd grade, but there are two factors of 72 that are different by 14. Okay, they need to be different by 14 because we have one of each sign, one positive and one negative. So as you start going through the things that you already know equal 72, like 8 times 9, that doesn't work. 6 times 12, that doesn't work. 1 times 72 doesn't work. So start dividing by other small numbers, like 72 divided by 2. That's 2 times 36. So those aren't different by 14. Does 3 go into 72? You try dividing, 72 divided by 3 is 24. But 3 and 24 also are not different by 14. How about 4? 72 divided by 4 is 18. There it is. So we want a positive 18 and a negative 4 because their sum is positive 14. So our factors x plus 18, x minus 4. And this last one over here, last one with negative 72, this time we want to sum negative 6. So we need different signs again because the negative on the 72, they need to be different by 6. So that is one of the ones that you learned way back when. It's 6 times 12, so we want positive 6 and negative 12. And I'm making the 12 negative because it has a larger absolute value, and I want my overall sum to be negative. So x plus 6 and x minus 12. Then 18. Again, we're using same C term, just changing the B term. Number 18, now we have positive 36. Since this is positive, we're going to have our factors be 2 of the same sign. Now, is that 2 positives or 2 negatives? That will depend on your middle term, your sum that you're looking for. So I want a sum of negative 12. Well, if I'm going to add 2 numbers with the same sign and have the answer be a negative, then these both have to be negatives. Okay. So what factors of 36 add up to 12? 6 and 6. So this one would be x minus 6 and another x minus 6, or x minus 6 squared. Now, number 19 happens to be the difference of 2 squares. I recognize that when I see the subtraction, it's a difference of 2, it's a binomial, and they're each perfect squares. I know the square root of x squared, and I know the square root of 36. So if you recognize that and can jump right to your factored answer, great. But if not, the method that we were using here in the last problem will still work. You just have to recognize that that negative 36 is your C term. Your B term, since I don't have an x term in the middle, your B is 0. So we need 2 factors of 36, this time different signs to get the negative. So one positive and one negative, that are different by 0 or In other words, the same number. So positive 6 and negative 6. X plus 6, x minus 6. And then number 20, we use our positive 36 one more time, and this time though, negative 15. So I want two of the same sign to get positive 36. To get negative 15, they're going to both have to be negatives. So what two factors of 36 add up to 15? That's 3 and 12. So x minus 3, x minus 12. And this last set of 3 here changes it up and makes it a bit more difficult, because now we have an a term in front of each x squared. So that means we're going to have to do more steps. We can't jump from that magic x right to our factored expression. We're going to have to do the key number method. So we still start the same way. We looked for a GCF. More important now, because of that 15, we don't have a GCF. So it's more important to remember how we really got that desired product was a times c. We sort of breezed through that last time because the a was always 1. So we just used the c term alone. But now the a isn't 1 anymore. It's 15 times 8. 15 times 8 is 120. We still take the b term for our desired sum. That's negative 26. So I need factors of 120, both the same sign to be positive, that add up to negative 26. That means I'm going to need to have two negatives. Well, I know you didn't learn any multiplication tables that had a product of 120, but it's a nice even number. It ends in a 0, so it's easy to pick out some factors, and it doesn't take too long if you methodically go through them, 1 times 120 and 2 times 60 and 3 times 40, till you discover that, oh, 6 times 20 is 120, and they add up to 26. Now, rather than call my factors x minus 6 and x minus 20, as we did in the previous 9 problems, we use these two numbers to break apart the middle term into two terms. So we're uncombining like terms. We leave the 15x squared, we leave the positive 8. But rather than write that middle term as negative 26x, I need to break it back apart using these two factors. It does not matter which one you do first, negative 6x or negative 20x, but those are the two terms that have a sum of negative 26x. And now I break this, since I have 4 terms, I look at it as 2 sets of 2. And I take out the GCF out of each of those sets. So in this first set of 2 terms, 15x squared minus 6x, the GCF, the greatest common factor, would be 3x. So I'm undistributing that. If I take 3x out, 3x times what is 15x squared? So that's 5x. 3x times what is negative 6x? Negative 2. Do the same thing with the last 2 terms, the negative 20x plus 8. Now, whenever this leading term of the second set, or the third term overall, whenever that is negative, you're going to need to take out a negative GCF. So whatever I find that goes into both of those, I need to take out negative. So what goes into 20x and 8? The largest thing would be 4. So if I undistribute negative 4 times something is negative 20x. That's 5x. Negative 4 times something is positive 8. It's negative 2. And what we notice here is this parentheses and this one match, and they have to. If you were able to complete this magic x up here, if you found factors that worked, then when you do the key number method, when you take out the 2 GCFs, these will always match. If they don't, you have made a mistake in between these 2 steps. So how do we write our finalized answer? We take that common factor out of these 2 expressions, which is 5x minus 2, and then we make one binomial out of the two GCFs. So we pulled out 3x minus 4. That becomes the other binomial. Again, it doesn't matter which one you write first, the 3x minus 4 or the 5x minus 2. No difference whatsoever. All right, let's do that again. Number 22. This time, when we multiply 15 times negative 8, we get negative 120. So that means my signs here will need to be different. And I now want a sum of negative 2. So I want factors of 120 that are different by 2. And that would be 10 and 12. Okay? Since I want a negative 2, I'm going to keep the 10 positive and make the 12 negative. Those two factors, again, are not part of your final factored expression. They are just used to split up the negative 2x. So negative 2x can be written as negative 12x plus 10x. Now, I told you it didn't matter what order you put them, and it doesn't. However, when you have different signs, one positive and one negative, I find it always easier to put the negative first. That allows you to avoid this step that we had to do in number 21, where we had to factor a negative GCF out. Right. The 15x squared still stays where it was. The minus 8 stays where it was. So the first two terms here, 15x squared minus 12x, what do they have in common? The largest thing I can remove from both would be 3x. 3x times 5x is 15x squared, and 3x times negative 4 is negative 12x. What can I remove from 10x minus 8? The largest thing I can take out of those two is a 2. 2 times what is 10x? That's 5x. 2 times something is negative 8. It's negative 4. And we see, again, just as we expected and needed to see, that the two expressions in parentheses match. So that makes one of your factors. The other one is made by combining the two GCFs. So 3x plus 2. And number 23, working with this 120 one more time. Let me move down here for my magic x. 15 times negative 8 is negative 120 again, meaning I will need factors with different signs. This time I want them to have a sum of negative 37. Now that feels like it's going to be much, much tougher, but if you're systematically going through factors of 120, you'll hit it pretty quickly. It's 3 times 40 is 120, and they're different by 37. So I want positive 3, negative 40. Just like I did in the last problem, I will write the negative 40x first, and then plus 3x second. It's up to you. That's my suggestion. 15x squared doesn't change. Minus 8 doesn't change. So again, we just broke up that middle term. What can I remove from 15x squared minus 40x? Well, both of those coefficients have a 5, or multiples of 5, and they each have an x. So 5x times something is 15x squared. That's 3x minus 8. Now, when I try to do that with the last two terms, 3x and negative 8 don't share anything other than a 1. We never list 1 as a GCF because 1 goes into everything. But when we're using this key number method, we need to write that just as a placeholder. It's plus 1 times, and we already have what we were looking to match in the first parentheses, 3x minus 8. So my factor's 3x minus 8 times 5x plus 1. And that, making this last final answer is why it's important to write the plus 1 there rather than just ignore it, because we need it down here. We need it in the second binomial to make that 5x plus 1. So number 24, looking back at each row of those factoring problems, so each row where we kept the a and the c the same, explain how it's possible for the coefficient in the middle term to be different numbers in each problem when your outside coefficients are pretty much the same, maybe changing a sign, but same number part. I'm not going to write anything there. I'm going to allow you to put that in your own words, but it has to do with using different factors, right? Building that number out of different factors. Here we build it out of -6 and -20. Here we use 3 and -40. Here we use 10 and -12. So when you change the factors that you use to get that product, it changes the sum or the B term.